Hey chemists, today we're going to look at more addition reactions to alkenes, specifically talking about hydration reactions, meaning we're going to turn pi bonds into alcohols by having a net addition of water. Water alone doesn't do this very effectively. We usually have other reagents, even just an acid catalyst, and I'll show you 3 new ways that you can do that. So the first one is called a hydration reaction with acid catalyst, and your product, if I use methyl cyclopentene, just as an example, gives you the more substituted tertiary alcohol. This is called a Markovnikov addition. Remember, Markovnikov's rule says that the H goes to the less substituted carbon, and the other group, in this case the OH, goes to the more substituted carbon. How do we explain that? Let's look at the mechanism. So let's redraw methyl cyclopentene, just using that as an example, but these work with all kinds of alkenes. The first part has H plus getting attacked by the pi bond. You form a carbocation intermediate. The pi bond is no longer there. And here's where the Markovnikov addition gets to be explained. A more substituted, more stable tertiary cation is formed, as opposed to a less stable secondary cation in this case. Then water sees that, the oxygen in the water attacks the positive charge on the cation, and there's your new carbon-oxygen bond. Now there's a formal charge of plus on the oxygen. All that's left to get to the product is to get rid of one of these H's. You could use another water molecule, have it attack one of those H's. This is just an acid-base step, and it neutralizes your product. That actually means you regenerated H3O+. So this is sometimes called acid catalyzed hydration, because you're generating acid and consuming acid, so acid is a net catalyst. This is actually the reverse of the mechanism we saw a few lessons ago, where you go in the opposite direction, where you start with an alcohol and you make an alkene. We call that a dehydration. Yeah, the mechanistic steps are exactly reversed. Now, depending on how strong the acid needs to be, you may not want to use that on whatever your molecule is. So there's other ways of doing this exact same transformation, like the second one for today. This is called an oxymercuration/reduction, and it starts with the alkene and this mercury reagent followed by sodium borohydride. You actually get the same product in this case. You get an alcohol, in this case the tertiary alcohol, and the mechanism is similar in the beginning. We have an alkene, this time attacking not an H cation, but a mercury cation. And you form a new carbon-mercury species. It's actually often drawn all as one step, where you have 2 new carbon-mercury bonds. There's actually a charge on the mercury, isn't there? And we call it a mercurium ion. I'm arbitrarily showing the mercury coming from behind the cyclopentene, but it could easily come from the front. So I'll put the little plus-minus symbol there to mean you get both enantiomers. But the addition in this part is selective, because it's on one face. Those 2 bonds have to be in the same direction. So when water sees this, it's actually going to attack one of the carbons attached to the mercury. This should look a lot like what we saw with bromine. Bromine made the bromonium ion intermediate. Iodine makes iodonium ion intermediates. This is the same kind of situation. We have a 3-membered ring that will pop open by something attacking one of the carbons. In this case, water is going to attack the carbon that feels more positively charged, the more substituted one. It opens up that mercurium ion, and there's your new carbon-oxygen bond. Notice it's actually from the opposite face of the mercury. So the oxymercuration step is stereoselective to add in an anti-fashion, and I'm going to keep it that way. Again, you have both enantiomers possible here, because I could have the reverse of these 2 bonds. I just arbitrarily chose the mercury coming from the back in the beginning. And then to finish this up, we're going to get rid of that extra H, just like we did in the previous mechanism. There's your neutral alcohol, but I don't want a mercury in my compound at the end. I want to turn that into just an H if I look at the product. So this uses a reagent called sodium borohydride, which looks like that. There's borohydride. That's an anionic boron with 4 hydrogens on it, and just a counter sodium ion. This will reduce the mercury down to a hydrogen. Now, I'm not going to go into the mechanistic details of how that works. So for this part right here, you can write down skip mechanism, because it's kind of beyond the scope of where we're at right now in this class. It's not necessarily selective for one face or the other. So even though the oxymercuration product goes with anti-addition, that new H could be in the same face or the opposite face, depending on the conditions of the reaction. So it's Markovnikov selective for regioselectivity, but there's nothing stereospecific about it with this example. Okay, the third one is stereospecific and regiospecific, and it's the opposite of what we've seen so far. This is called hydroboration oxidation. It also turns an alkene into an alcohol, but you have the opposite regioisomer. This is a constitutional isomer. I have the alcohol on the less substituted carbon, so this is a non-Markovnikov addition, sometimes called an anti-Markovnikov addition. And it is stereospecific where the new H and the new OH add to the same face of the alkene. So you get a selective syn addition. I'm arbitrarily showing it from the back of the screen, but it can easily be from the front of the screen as well. How do we explain this? Let's go through the mechanism. So here's our cyclopentene. The first step is it sees borane, that's BH3. And in one concerted step, you form a new carbon-boron bond, that's the alkene pi bond attacking the boron. At the same exact time, the boron hydrogen attacks the other carbon, the more substituted carbon of the alkene. This is mostly just a steric argument for why it looks this way, so that the product, or I should say the intermediate, has the boron attached to the less substituted carbon, and the H is on the more substituted carbon. That's what's going to explain the syn addition. How do we turn this boron into an OH? That's where peroxide and base comes in. Actually, there's a few steps I'm going to skip. I don't think they're important for this part of the mechanism, but because there's other boron hydrogen bonds here, in this case 2 others, other equivalents of the same starting alkene can actually react with those, and you can have a single boron atom with 3 of these hydrocarbons attached to it in a nice symmetric arrangement, but they all end up cleaving from the boron and turning into alcohols. So I'm just going to show that for the one. So when you have peroxide and base, it's simply the conjugate base of peroxide, HOO-. That will attack the boron, and you get an intermediate with a negatively charged boron atom and a new peroxy attached to that boron. So how does this become the product? Well, this collapses sort of on its own, where the carbon-boron bond right here breaks, and those electrons attack the oxygen of the peroxide, and then the peroxide bond, which is a notoriously weak bond, breaks and kicks out a hydroxide. We're under basic conditions, so it's okay to kick out a hydroxide leaving group. That turns into an intermediate that looks like this, where you've essentially inserted an oxygen in between the boron and the carbon, which we bonded earlier in this step. How does this turn into the product? Well, we've got that hydroxide floating around. That will attack the boron and kick out the oxygen that we just inserted between the carbon and the boron. So you start to make boric acid species, borons attached to OHs, but more importantly, you make the conjugate base of the product, this alkoxide. To wrap up, we just need a source of a proton. In this case, it's water. We're under basic conditions, so there's no H plus around. But water will donate an H to that oxygen anion, and that's how you get your new secondary alcohol. So all of these turn alkenes into alcohols. The first 2 are Markovnikov, and the third one is non-Markovnikov, and the third one is selective for syn addition. You can make a note that none of these are enantioselective. We're starting with achiral stuff. So when I draw this product of the hydroboration, yeah, you get the enantiomer as well. In other words, it's going to be a racemic mix. There's 2 new asymmetric carbons in this particular example. Okay, so to wrap up, let's show just an application of one of these reactions where we just make one subtle change and you get a completely different looking product in the end. So here is an example of what's called an alkoxymercuration. It's almost the same thing as an oxymercuration, but we have an alkoxy group. The difference is there's an alcohol instead of a water molecule. It starts the same, where the alkene attacks the mercury. You get an intermediate mercurium ion, and then instead of water opening up that mercurium ion, the alcohol opens up the mercury, still attacking the more substituted carbon. That carbon-mercury bond breaks, and you get an intermediate with a new carbon-oxygen bond, and there's like an alkyl group attached to it. Instead of 2 H's, I have an H and the ethyl. Then we're going to get rid of that extra H. I could use an ethanol to do it. This looks just like what we have up above, but we're using ethanol instead of water. There's your alkoxymercuration product, anti-addition because of that mercurium ion. But just as we saw before, the sodium borohydride will reduce that mercury, and you get a new O-ethyl attached to the more substituted carbon. which is actually an example of an ether. You now know how to make an ether. I think that's the first time we've seen this since acid-base SN2 days back in the previous unit. Okay, so there's 3 new ways we can take alkenes and turn them into alcohols, and you can tell by modifying the middle one by using an alcohol instead of water. You get ethers instead of alcohols. They are selective regioselectively, Markovnikov or non, and the hydroboration is quite stereoselective, giving you syn addition. Thanks for watching.